several things come to mind in it. It is helpful to understand what you're trying to control. You know, when you have a target in mind, because that's what control means, is that you're heading for some target. And you really have to have an understanding of the system of some sort, in a rough sense, to at least know where the target should be, what to do. A lot of times that, you know, at work, when it comes to technicians, it's not only helpful to be able to do jack a motor, handle tools, replace a part, but also what's involved. What's the system doing? What's important, what's not important? But it gets around to control, we get a lot of this. Actually, the test gets a lot of this, is that there's people who know how to do control systems, programmable computers, but what are they trying to do with that program? Many times don't have a clue. There's people who understand the process, but don't understand how to control it. Computers are a mystery too. The ability to combine the two is a valuable skill. Thinking back, probably sadly, the last 15 years of my engineering career was based upon I could program something to control something I understood. That sounds so simplistic. And a lot of people don't do it at an engineering level. That's an amazing characteristic. Like last year I got 3 calls for jobs. I didn't apply for a job. They caught my 2011 resume somewhere floating in the internet there and made cold calls to me. I get about $75 to $100 an hour doing that sort of stuff. Specifically, it's testing wireless routers, which everybody has a wireless router in a house by now. Actually, your phone is a wireless router. It could be a hotspot. So how simple can that be? It is simple. I'll tell you right now, if you think it's complicated, it isn't. But the people who understand the RF usually have no clue what to do with a computer. People who understand computers have no clue what to do with RF. I don't have to be good at either one. I just put the two together. That skill alone is worth, in the open market right now, about $100 an hour. You know, people talk about medical school, law degrees or something like that. So making good money in this country is very easy. It just takes, do it. That's all it takes. Really stick to it, decide that's what you want to do versus what you are doing. It's as simple as that. In any case, closed loop control systems. Not enough, I don't consider myself a hotshot by any means. I work with tons of engineers who are better engineers than me, smarter than me. I work with a lot of people smarter than me. Various ranks. I've known a lot of smart people that don't do very well either. There's lack of application. It's interesting, over many, many years I've been involved in teaching education, the vast majority of letter F in grades did not come from lack of ability, it came from lack of effort. And almost everybody thinks they put in more effort than they do. You know, you count the number of hours you spend, say, a night per night working on something like this. You know, it's not 10 hours or so, it's, you know, you can put more hours. It'd be amazing how many hours you can put into something if you really want to. It's kind of like hunting trips. You go hunting. For that week, how many hours do you spend per day? A whole lot. Hey, it's fun. You want to do it, you want to be good at it. You want to bag that deer, bag that bird, bag whatever, bag the fish. It's fishing. It is an effort. It's joyful to do it. People do a lot of it. That's the sort of thing you bring to work. And I would say, you know, work should be interesting. Oh, you know, one of the things about school is your chance to actually see parts of a job. That's what tech scholar is such a great thing to do. Because I have people that have done tech scholar and after 6 months or 12 months say, you know what, this isn't for me. We've had that, and that's great, because at least they now know what they don't want to do. Because I almost guarantee, probably about 95% of 18-year-olds coming out of high school have no idea what they want to do. The other 5% have a little bit of an idea. Sound familiar? Absolutely. Because I mean, what are 18-year-olds in this country exposed to? Education, teachers who half of them hated their jobs. That's something that needs to be fixed. That's an attitude adjustment, I think, in most cases, frankly. Hopefully, didn't see too much of the police, because that's usually not a good thing, or the fire department, or doctors, because that's again not a good thing necessarily. And other than that, they just hear their parents bitching about their jobs. So, how to get excited about something? So it is difficult. I mean, you all have that hunt, that's a difficult job for you. Part of it is, school here, hopefully we're exposing stuff, and it's of interest, great, wonderful, you make a fabulous career out of this. We've had a number of people, got excited over this stuff, did it, and, doing very well. Really well. Hopefully, after you get out of here and teach, you should all be making more money than me. That's a reasonable expectation, 1 or 2 years down the chute. A lot of you right out of the chute. So money shouldn't be an issue. And that shouldn't be the number one reason why I went into maintenance. It should be, you found it interesting. I'll tell you what, if you don't find it interesting, your life's gonna be miserable. You must, get the usual bit. If you work 40 hours a week, and you drive a half hour to work, you take a half hour lunch, you figure that's about 55 or so hours. If you sleep on the average 7 hours a day, of your waking time, out of a 128-hour work week, you soon figure that, you spend more than half your time at work. Really. Mm-hmm. You'll spend more time with work than you will with your spouse, your girlfriend or boyfriend, or significant other or whatever, your hobbies. You'll spend more time at work. Hopefully work is interesting. I didn't say fabulous and most exciting thing in your life necessarily, but interesting at least. If it's not interesting, or you hate it, it's gonna be miserable. So it's one of the things, get out of here is, is this something you really like and are interested in? If not, you need to find that. Now, I'm finally getting on the class. Sorry about that. You should hear that from somebody. And it just got a reorientation of, is this what I want to do? Or am I still looking? It's okay to look. Hopefully by the age of 40 or 50, you found it. The sooner the better, from the standpoint, but it takes what it takes. And it's okay to have more than one career. I mean, I consider myself to have 2 careers, probably three is closer to it. One is an engineer, which is my primary one. The second one is education, teaching. I've done the administrative bit in school, and I'd much rather do the teaching part. There's other people who do administration. Let them play around with it. I do get picky about teaching. You don't see me teaching philosophy or sociology. That's not going to happen. There are better people than me for that. And we have them here in school. But technical stuff, this is interesting to me. That's funny, after about half a century, it's still interesting to me. Industrial electronics, closed loop control systems, a little bit more of the overview bit before we get into the details of it. Process, a measurable output. A process has a measurable output. Actually, a process has an output. I shouldn't say necessarily measurable or not. But the target here is to have any control, we're going to have to have a measurability. We're going to be able to say good, good, gooder, goodest type of thing. So most industrial processes have real targets for the process to complete, like temperature in a room or oven, flow rate, level speed, kind of like a thermostat at home. So it's winter time, what is you doing at your home? You have some source of heat coming into it. Either that, you're wearing a whole lot of coats. Or chopping wood, something which is generating heat also. How would you control the amount of heat in your house? Thermostat. And what you do to the thermostat to control the heat?
Turn it up or down.
You do set a temperature. So in that system, what's your target?
Temperature.
That's really the temperature. You can measure temperature. Use that as your measurement. Now, is that truly the output of your furnace? Your furnace is heat, hot air. It's really heat, it's not temperature. It puts in heated air and it mixes in with the colder air in the house or home or apartment or whatever. I should use the word home, that's all inclusive. And it mixes to a temperature which we measure, and that's what we use to estimate a comfortable amount of heat versus an uncomfortable amount of heat. Uncomfortable being either too warm, too cold, they're both bad. That's an idea of a real target, is we've established a real target for using temperature because we can establish a pretty reliable measurement of temperature and a pretty reliable control based upon temperature. So that's why it's a chosen variable for that. We're gonna run the variable shortly. Odds of achieving goals need to be optimized. In other words, whole thing about control, again, as I mentioned, optimization or optimization of hitting a goal. I don't like to use the word maximize because you may want a minimum thing. Like the amount of work it takes to do something. Optimization would be minimize that. Optimize is really a better term. And that involves usually adding a control loop. That's a closed loop versus the open loop. Your basic control loop. It was looking awful, like I said 2 days ago. There's a different view of it. Process of measurable output. Here's a process. System input directs a target ideal process output. So amongst other inputs into it, we'll have some sort of a reference, whether it's mechanical, electrical, operator set, thermostat setting, and the setting of a set point would be basically hit the plus and minus buttons to get the number you want. And a control loop, which is a controller added to the basic process to optimize achieving the target we want, the output that we want. Now in the process itself, we have usually motor, valve, switches, something in here that we're trying to control on a process. Feedback, that's a closed loop. We look at the output and say, are we there yet? And then from here, make adjustments to the input to try to force this to do something. Finally you see the word valves and switches, and it's going to see sensors here. That gets to be a large part of the process control. A little bit about motion classes or control classes. There's really about 3 or 4 different loops from a system standpoint, a block diagram standpoint, that everything falls into. There's motion control, process control, and batch and continuous. Now I usually like to put in here level versus accumulation as well in the process. The motion control type of stuff usually winds up being more driving a car, moving a vehicle, that sort of thing. And we could have things like velocity, such on. Your process things, the more common ones you really have in making a product, is a product usually something you can ship. Temperature, flow, levels, pH. It basically really comes down to, you can have a flow parameter measurement or a level, or what we call analysis, chemical analysis type of thing. And the flow and level is really the 2 big ones. Our stands and tests will do that. You'll see that ultimately. The difference between flow and level is flow is instantaneous. If I'm measuring the flow of water, that's in gallons per minute. You fill up your bathtub, at home, you can adjust, I want a high flow of water. You turn on the faucet heavy, a lot of water comes out. Secondarily, what are you really interested in the bathtub situation usually is the level. Now, in achieving a level of water in your tub, does it directly matter how fast the water goes in?
No.
It doesn't directly as far as the level of water. It does how long it takes to achieve it. The higher the gallons per minute, the faster it is to fill up your tub. So you usually turn on a faster flow, but ultimately if you're controlling the level, the flow is a secondary thing. That's to optimize the time it takes. But you still need to control the flow to get to the level. A level is something we refer to as, engineering time is integrative process. You don't need to know that. Basically, a better term is accumulation. So in flow, it's gallons per minute. That's an instantaneous number you hit right on the shoe. A level is gallons per minute times minutes. The minutes divide out, minutes over minutes divide out, and you're left with gallons. So you can see it's an accumulation of flow to get to the level. But something that occurs over time. That's just something I mentioned now. Towards the end of the course, I'll mention it again, and at that point, then we'll start to say, okay, what's the difference? And you'll see it when you calibrate control loops. Then you get the integrative effect versus just the instantaneous effect. It does make a little difference there. That's kind of a first exposure to it, and it's like you'll wake up again, and I'll talk about it back then in April. Will make sense. Batch versus continuous. Batches are when you make a single product. It could be a group of products. You make it in one shot, boom, the process follows that. When it's done, it's done. Put it aside. Then you make the next batch, if you need to, and produce that. We mentioned something like, ovens. You bake, say, a bunch of cookies, and you make an oven's worth of cookies, and you stop, put them aside, and you make the next batch of cookies. And limitation usually is the size of the oven you have at home. If you're cooking, say, 6 dozen cookies for people, you probably wouldn't make one big batch. You'd make about 2 or 3 batches. It's still a batch job. The continuous flow is something that just everything keeps running all at the same time. I mentioned the printing of newspapers because you make, say, the Washington Post newspaper, lots and lots of newspapers, the printing press just keeps rolling, one paper after another. You're making toilet paper in Kimberly-Clark, it keeps running one right after the other. It's not really a batch. And the problems here is that in batch, you can kind of stop the batch and roll. Actually, you can stop continuous process too. But the continual monitoring means it never really slows down. The batch will have some slowdown. A lot of commonality, but there is some timing differences in there. The bigger issue, open loop versus closed loop. In an open loop system, we don't monitor the output. In a closed loop system, we do. I'll mention, the concept of let's feed forward. Concept I haven't had. Feed forward is a system where the output achieved is estimated based upon the inputs. Ignoring any measurement of the output. It's open loop. We don't ever measure the output to say, are we there? We sit there with a system, do something, and say, it's probably it. It's kind of like if I follow a recipe for baking, I'll pick on something, pancakes. I go to the box, Bisquick, it says, so many cups of Bisquick mix, so many cups of milk, so many eggs, so many tablespoons of oil. Throw in the vat, stir, pour on the griddle, make pancakes. No adjustment in there for, gee, the pancakes aren't coming out too thick, pour more milk. Coming out too thin, throw more Bisquick in it. Nothing like that. Just simply a fixed recipe. If I do this, I should get the output. Is there any measurement or quality output of the quality of the pancake I'm getting? No. Not really. I throw it on a griddle, it looks kind of hard, flip it over, it looks kind of hard, throw it on a plate, it gets eaten. That's an open loop system. I don't use what's coming off the griddle, maybe the thickness of the pancake, to adjust the batter for the next pancake. Now, if I did that, then it would be a closed loop system. We would be looking at the actual output, measuring, and it might be a qualitative measure. In other words, no number sign. It looks too thick, it looks too gooey, it looks too thin, to make an adjustment to the batter. I don't do that. I just simply have it mixed according to recipe. That's it. That's the way it's going to be. You know, for good, bad, indifferent. That's an open loop system. Now here they use swimming pool filtering as an example. No correction for problems in a swimming pool. Now, swimming pool filter, literally, you have a swimming pool. Maybe you personally don't, but somebody has a swimming pool, maybe your apartment complex. It has a recirculating pump that recirculates it through a filter. That filters out the leaves, the dirt, dead animals, whatever's in the pool, frogs. Does it ever adjust for anything? Do we adjust the pump rate through the filter? No. Does the filter have to be manually cleaned out eventually or changed out? Usually. There's no automated system for that. That's an open loop system. For most pools, it works fine. You jump in your apartment complex pool, and usually the dead frogs in there haven't been dead for more than a day. So there aren't that many of them. Too many leaves to jump through, and it's because the filter system seems to be what we call working. Now, is it perfectly optimized for what? You know, you probably measure it by how many dead frogs are in the pool, or how many leaves in the pool, and it seems fine to me for diving, so I guess it's optimized. Open loop systems can work very nicely. It's not so-called the best for keeping very tight control on money when it's down to, 1% makes a difference, performance maybe wise. It's not going to do that usually, but open loop works pretty fine for a lot of things. Filling up your car tire pressure. That can be optimized, optimize your gas mileage, that sort of stuff. How many times do you check your air pressure, your tire?
When the light comes on.
When the light comes on, if you have one of those. You don't have a sensor built in your truck. You wait for that. That's a good case of open loop system. You're not constantly checking it. Adjust it from summer to winter, for instance, where it drops a couple PSI. So I'm pretty sure it's not optimized. Which means either it's a little underinflated or overinflated right now. Probably underinflated now, or no, summertime be a little overinflated. No, that's a case in point, but it works fine for you all. I haven't heard anybody complaining about too many times about flat tires. Something like that. Closed loop. Feedback built in. Feedback is we take the output measurement and bring it back to the input control. That's why it's considered to be a feedback. Whereas feed forward only goes one direction, forward. Feedback goes backwards. If you think of left to right flow. Float switch and a tank refill. By adding a float switch and filling up a tank, what happens? If you use that, it's kind of like your toilet at home. You flush the toilet, the water magically stops, doesn't it, after a while? The first thing you hear is a and the water disappears out of the bowl, but because the water in the tank got released, that creates a vacuum, which is just like siphoning, sucks out the water out of your tank because it has to go uphill before it goes downhill. There's a little less curve in there than a toilet. And then eventually it stops. What stops it? Of course, the float switch. So toilets are made. They have a valve in there, they have a float switch. And a float switch is a measurement of the water level inside the tank. So that's a feedback system, so it's a closed loop system. It's not just time, so many minutes of water coming in. It's done off a float switch. That's a case of output measurement. Could we just time it and rely on that? Probably. Maybe the float levels of the toilet would be a little less accurate, but it's cheap enough to put a measurement in there and certainly keeps it from overflowing the tank a little bit more, so it's probably worth it. That's where decisions are made between open loop and closed loop. If the money trade-off is such that closed loop cost, because it does cost more, is paid back in optimization, then normally we do it. If not, then we don't. And that's what really the decision between open loop and closed loop comes from. Some terms. We get to the terms of loop, and these will appear a lot in talking through things. A control variable is your output of the process that you're concerned with. Well, actually, will be controlled. As opposed to manipulated, this is what we're trying to change. For instance, we have a flow system. We have so many gallons per minute flowing, and that's what we're trying to control. Let's say I want two gallons per minute. Now, ultimately, I may be filling up a tank, and I'm really worried about the tank. But right now, to get 2 gallons a minute, I'm trying to control this. So my flow rate is my control variable. To flow through here. Ideally, 2 gallons a minute. What is it really? It could be 2, it could be more, it could be less. Could be a negative number. If I have 2 gallons a minute, is my target, and I measure minus 1 gallon per minute, what does that mean? Always hear from me, numbers should mean something. If it means nothing, then who cares? It's kind of like jitter in Chinese. What does the minus 1 gallon per minute mean? It would mean you have 1 gallon per minute flow in the opposite direction. Now, usually when you have a negative number, it means change the polarity, so to speak. It's electrical, battery voltage, minus 12 volts means you reverse the cables on your car battery. Here, minus a gallon per minute means you're going in the opposite direction. Is that possible? Maybe. Couldn't guarantee it, but possibly. It's not possible, like you have a check valve in the system, it should be at lowest 0 gallons per minute, at most some positive number. But the number again should mean something. And I'll put it in a process. In this case, I want 2 gallons a minute, that becomes my controlled variable. That's what I'm going to directly try to control. Now, if I have a level system where I'm trying to control the level, I may have a secondary control variable, also called flow rate. How fast do I fill up the bathtub? So I have 2 things in my control. Nothing to say we have 1 control variable, we can have multiple ones. Next thing, set point. Set point, command, reference, all the same thing, set point. Input to the system directs the target process output. A lot of big flowery words. It really is our desired target. In this case, that's specifically 2 gallons per minute. Keep in mind, the control variable is flow rate. We don't know what the flow rate is yet. The flow rate is what's actually here, the actual flow. Our set point, if I desire 2 gallons per minute, that's the set point. The set point is not necessarily achievable. It's what I want the output to be, the process to be. If I want to say I have a certain flow rate, like an irrigation system in the yard, I need to put so much water out there. It's a flow rate. I have an established flow rate. I've set things for that. That's a set point. Do I achieve it? Don't know. That's what the process control is for. is the flow rate that I'm trying to control, so that becomes a control variable. Actuator drives the process output from the input. In a control system, the input is first modified control. A lot of fancy words here. Commonly, small motors, pumps, louvers, valves, or switches. In other words, an actuator, for those of you in hydraulic pneumatic class who know this, cylinders, hydraulic motors. The actuator is a thing that actually does the mechanical work. Is what moves. So your actuator is a little device in here. For a moment, I'll put a valve in here, gate valve. That's called an actuator. It's what we move or change to achieve what we want. It's a device to be controlled. Because if I want to achieve 2 gallons per minute, and I have a valve in there, what do I actually physically change, maneuver, whatever, to achieve 2 gallons per minute? I turn a valve. It's like my bathtub at home. I want to fill it up with water, what do?
Turn it on.
I go to the handles on the spigot, I turn 1 or 2 of them on, usually both. I turn them on, and that's flow going in versus flow not going in. Those are actuators. Measured variable. Estimation controlled variable. It's what measures the variable. Now, as I said, I don't know what the flow rate is here. If I want to know what this flow rate is, what do I need to do? Put in a flow meter. So I attach in here. I'll do this in blue, I guess. There are a variety of flow meters available. You can use paddle wheels, you can use radio. Some don't make contact with the fluid, some do. We do have a couple of them on the process control stand out there, as you can imagine. This winds up getting, this measures our measured variable. In this particular case, it matches our control variable, the flow rate. It doesn't have to do that necessarily. Examples like my bathtub, if I tend to set my bathtub and fill it up, I plan to be somewhere else and come back later, I might be setting a flow rate, I might measure a flow rate for that matter, but it's a level I'm interested in the tank. I'll use flow rate times time to figure out how many gallons I have. That's a case where the measured variable, the flow rate, doesn't match what I actually want, the level. In this case, it is. I want 2 gallons a minute. I have a pipe, I have a valve to adjust my actuator to get whatever flow rate I have. I measure this to see do I achieve it or not. And in this system, you can see what's coming up is G. If a measurement says I'm not doing 2 gallons a minute, let's say I'm getting 3, what do? I go back and tighten the valve. If it's saying I'm at 1 gallon a minute, what do? I go back and open up the valve a little bit more. And I keep going back and forth until I measure 2 gallons a minute. So I have here a set point, I want 2 gallons a minute. I have a controlled variable, the flow rate. I have a means to control gate valve opening. I have a flow meter to actually do a measurement on the output, so I've added that to it. Now a controller generates a correction from the error signal. What's the error signal? Well, desired set point minus a measured variable equals the difference. That difference is the error signal. Now say my flow rate's too low, the controller then, me, in this case, not saying it could be a person, so it says I need to open the valve. If the flow rate's too high, it's a negative difference. too much, it's a negative number, I need to close the valve. That's the case of doing this. A disturbance is anything that alters the process. First thing comes to disturbance here. What if a big chunk of metal comes in here and clogs up the pipe? Would that change the flow rate?
Yes.
Probably. In which case, then I have to clean out the pipe or open the valve even further. But what happens if I set this whole thing up, there was already a chunk of metal in here, and now it breaks free and flows out. That flow rate flies up. I gotta readjust. If I put screens in here to filter out crap, that's a good case of things that change. There's a lot of what we call disturbances. These things, and a lot of them come long-term, equipment wear, noise inputs are more direct. It's anything that's not planned for. That's a disturbance. If something makes a change on the fly, not directly controlled necessarily, usually not directly controlled, those are called disturbances. That's a fancy term for it. The controller is what's going to run this loop to make those adjustments. Some terms here, feed forward. Feed forward is when we estimate the output from the input. That's how we get our estimation of the output instead of a direct measurement. We look at our input, I call it input variable for numbers. It's a guess as to what our output would be. We might say I've set a flow rate, I count time to estimate how much gallons of water I moved for a level. But forward means forward direction. Feedback is when we usually measure an output of a system and run it backwards to help adjust the inputs. Error detector. That's our comparison point to set point. In the case of this system, it's manual. I look at the flow meter output, might be a gauge. I want 2 gallons per minute. I mentally in my head subtract the measure from its tube, and that tells me which way to go. If it's a positive number, that means I need more flow. Open up the valve. If it's a negative number, I'm getting too much flow. Close the valve. Now, I could have a PLC do this for me. I could have a computer do this for me. They just take my place. Not to say these systems can't be manual. They can be manual, they can be automated. Almost all automation is based upon this concept of manual closed loop. Because without measurement, there's not a whole lot that automation will do. Again, your basic control loop looks like the same sort of a block. Process a measurable output, system directs a target, control loop corrects to follow that target. What do closed loops do? Whole purpose is increase accuracy. A closed loop is almost always going to be more expensive to put in than an open loop. It involves more equipment. It's got to be more expensive. It pays for itself by optimizing better. Typically it will do that. It's just a matter, is it worth doing? You know, and ultimately there's a cost trade-off. That's why we have imperfect systems. Could we have a perfect bathtub filler in your house, in your home? Automated, you push a button, bathtub's automatically filled at the correct level? Sure you could. Is it worth it to you to put it in your tub?
No.
For most people, it's not. You got 5 minutes to check the water to see if it's in there, and that's good enough. So it's a manual process. It's not worth it. How many would you like to have a Lamborghini to drive? A lot of us would.
Corvette.
I'm not talking about money, I'm just talking about Corvette. Okay. Versus what you're driving now?
Yeah.
Sure. I think we all have a target, an ideal car, or vehicle, or truck, whatever we really would like to have. You know, all things aside, if Elon Musk came and said, you can have the vehicle of your dreams, what is it?
Blue
And he gives it to you for some reason. Kind of like Oprah Winfrey giving cars to everybody in her studio. She did that one time. You know, when you get that kind of money, you can do that. Be like Santa Claus. Okay, what stops you from getting that vehicle right now? Probably 100% of the case here, money. It's not worth that much money to you. So I pick on Lamborghini there. I mean, I've seen a Lamborghini, it's a nice looking car. At the time, was it worth $250,000 it cost? Not to me. the Washington Redskins football players it belonged to, yeah, it did to him. Difference in value. So value is a big thing. So a closed loop does get some accuracy in here. We can measure to it, and this is the perfect example of it. Now, if we want, say, 2 gallons a minute, and we can measure precisely times 1, that's fine. We get it. If our process changes by 10%, and we have a totally uncontrolled system, our output changes by 10%. In this case, like the valve gets a little bigger, a little smaller, clogged. What does closed loop do? We actually measure, instead of times 1, we measure it, we take a feedback, we put it in here, desired output minus actual output to reset our control to try to bring it back in line. Now we're using the error in there to adjust. Now I didn't have numbers here like 0.5 and 2. And what that really does is it emphasizes the set point over the feedback. We can adjust those to have more feedback control, less feedback control. And there's reasons for that we'll discover later on in April. We won't do it now, but the concept being is this loop allows us to monitor the output, adjust our input to hopefully get closer to our target. Now I've got a bunch of fancy names in here. In green, set point, error, control variable, measured variable, process variable. And what are these things? And notice it says SP, PV, E, CV, and notice I have this MV for measured variable. I can throw another one in here called manipulated variable as well. Leave this system in here. Set point, that's our target. I set it. I chose 2 gallons a minute. Usually we choose it, and it's above and beyond the process. It hopefully is within the possibility to process, or sadly we're never going to achieve. But assuming we're going to have something realistic, it's achievable. Error. Error is the difference between what we actually have and what we choose. Notice it said process variable. If it's a flow rate that I'm really trying to get through here, probably our process variable is flow rate. Is our actual output. In this case, the flow rate. Getting so much flow for whatever the system needs. Small little loop. Provide so many gallons per minute. Process variable in this case looks an awful like the control variable, measured variable, and a few other things. Many times it is that. It's all one thing. Many times it is not. Now the process variable is what we're really actually trying to retrieve here. It might be the flow of water. Now, it may or may not be directly controllable. If it's directly controllable, then controlled and process variables wind up being almost practically the same thing. The measured variable, if we can measure directly the process variable, that's wonderful. That's ideal. This is the best we can do, the best we can do for control. We may not be able to do that. Like for instance, my process variable is really the level of water in my bathtub, but all I can measure is the flow rate of water going into it. My measured variable is the flow rate. My process variable would be the level, and I use the measured variable to estimate what my process variable is. Hopefully, pretty close. You have to do an estimate, and that's, you wind up with an estimation. You want to make your estimation as close as possible to what's actually there. That's the source of an error in the system, one of many errors. In a perfect loop, we're using the process variable and comparing that to our set point. Our set point is always the process variable. Since here, my set point is 2 gallons per minute, that sets a flow rate, so I know my process variable in the system is flow rate. Whether I measure it directly or not, or indirectly and estimate it in material, that's the relationship. Set point is in terms of process variable value, what I desire that value to be. Process variable, what is the actual value? So those two are directly related as far as what are they? The measured variable is what I can actually measure versus what the process variable is. If I can measure the process variable, that's always preferred. If I can't, I measure something that has a pretty good correlation, so to speak, with the process variable. Controlled variable is what I control going into the process. If I want to change flow rate, I have to control flow rate. That kind of sounds, sometimes the control variable is your process variable. In this case it is. If it's level, I control the flow rate still. So that's the case. The control variable and process variables are different. Something I didn't mention here is manipulated variable. That's an L. Manipulated variable. That's what we directly change for control. In this particular system, here's a little question. Is my manipulated variable the same as my control variable? That's going to be a yes or no answer question. And many of you will say yes, and you will be incorrect. What are we actually manipulating here? The gate valve opening. So when I want 2 gallons per minute, and I do or don't have it, what do I change? I don't change the flow rate directly, I change the gate valve opening. So the gate valve opening is my manipulated variable to control my control variable, the flow rate. The valve opening controls the control variable. That control variable then leads directly to the process variable. It's the same thing, so it makes it really tight coupling. The measured variable with a flow meter happens to be the process variable as well, so that's nice and tightly controlled. The controller directly changes, in this case it's me, the valve setting. Usually in a system, when you see valves, whether they're solenoid valves, whether they're adjustable valves, you'll get both the hydraulic pneumatic stands on there. You do have an adjustable valve on there, on a hydraulic stand. I can picture it. Most of the ones in there are going to be your flow control valves are adjustable type of thing. They're valves. The directional control valves, like your 4-2s, 5-2s. Usually it's your 5-2s, 5-3s of pneumatics, and hydraulics tend to be 4-2s, 4-3s. Those are valves. Those are also, but they're yes/no type of thing, on or off. That's still where you're doing controlling. So the adjustment of those valves is literally your manipulated variables. The state of the valve. If it's an open-closed valve, is it on, is it off? What flows through it is usually your control variable, whether it flows going through or not. Your manipulated variable is the state of that valve, because that's what your controller does. Your controller turns on or off the solenoid actuators into that valve. So that control of that valve direction or control of that valve opening is your manipulated variable. You don't measure that typically to look at your system. Usually what you measure is the control variable, which is the flow through it. Are you getting flow or you're not getting flow? Now, if it's an adjustable like a flow control valve, you probably do measure how much flow you're getting through, maybe. That's the difference between manipulated and control variable. Other than that, the terms tend to be around the process variable center. Now, process variable, like in a cylinder case, may just be you want the cylinder extended versus retracted. If you want extended and retracted, the state of that cylinder is really your process variable. Would you measure it? You might measure the extension on the rod directly. That's great. You have a measurement of the process variable. But if you don't, you look at the error, when the error is turned on, and for that, it's a measured variable, you have a pretty good estimation whether the cylinder succeeded in extending or retracting. Now, is it perfect? No, something may be hanging up the cylinder. The error says it's going in a proper direction, but the cylinder can't fully extend because something's blocking it, locked up system. That's where you have a process variable and a measured variable difference. Where a measured variable isn't a good estimation. So I mean, this says, not perfect. If you could measure the extension itself, like a limit switch, like you have available in those stands, then you do have a very good measurement of that, extension versus retraction. So in the systems, now I've used a lot of this, that, and the other. The overall message here is, recap on that. You have a set point. That's what operator desires. I'll call operator, person operator desires. That's set regardless of whether it's achievable or not. We look at some estimation of the output. Usually a measured variable is our beginning of the estimation. We may have a mathematical adjustment for that to come up with an estimation of process variable. We compare set point of the process variable to the actual process variable value. And the difference between those two values is the error. That will drive the controller to make an adjustment. That adjustment means it manipulated variable, something like a valve opening typically, or relays to turn on and off motors, to make that adjustment to the process input so that it comes closer to the output we want. Control variable is what we're controlling. Through the manipulation of the valve, we control a variable like a flow to achieve the process variable's value that we desire by set point. And again, we measure it again. Notice it's a loop, we keep doing it. Process control things tend to be constant. They keep running, never ends. Accuracy numbers, a little bit of mathematical. I don't want to really go into that today. I'm not interested in sharing that part of it there, but through loop numbers as far as measurement, control, that sort of stuff, we can adjust it to get a little bit more accuracy out of the system. I'm not worried about that one. But in this particular example I had here, just to show, if we had a 10% error, the change in the output would get hold to about 5.3%, 4.7, in other words, we cut it in half using the numbers I had in there for the loop. So there are adjustments in the loop. That's this particular set of adjustments. I can make more adjustments that get tighter or looser. That's a subject really for April, where we talk about loops and adjustment, calibration of the loop to minimize this error, which is the system closed loop error, versus the open loop error. Open loop error is whatever the process generates. The closed loop wants to put this as an error so that we get to the output within this tolerance rather than that tolerance. Tighter tolerance. That's the whole purpose of closed loop, is we can usually achieve a tighter accuracy, get closer to our desired output. Whatever desire is, whatever we're trying to optimize. Mathematically, fairly well proven. Probably we'll get through. It's really not a whole lot of math involved. I do have a PowerPoint here, but that's something to get more into in April. We'll have you go through a couple examples of calibration of loop so that you can see it. Technicians do get involved directly with this calibration stuff in the process, so do want to see what you're trying to do. A little bit of dynamic response, but subject for another day. You can see these PowerPoints online. Everything I give in lectures here is online, so it's on Blackboard. Any questions? That's kind of an overall pop, whistle, and bang. I don't expect you to know all this stuff right now, but it's the opening thing on loops to just start to work. Okay, where do we see this stuff? So we'll pick things back up on Monday and